Hi guys, welcome back to the channel. Hope y'all are doing well. Today we're going to design a system similar to Facebook's Find Nearby Friends system. You can see screenshots of it over here. Before we get into the design, I have a few housekeeping announcements to make. The first one's going to be that most of the design that you see in the video has been taken from the book you see over here. It's called the System Design Interview Volume 2. I would highly recommend checking the book out if you are interested in system design. In this video, we're gonna talk about things on a pretty high level, but the book does an amazing job of going into the details about each and everything that we're gonna talk about in this video. The second announcement is that I know that in the past 2 to 3 weeks, I have not been very consistent with uploading the videos. It's gonna change starting the coming week. The plan is to upload a video on Monday and one on Friday. So you should expect 2 videos going out every week. On Wednesday, I am going to be uploading a Medium blog post. I will have my Medium link in the description below. If you want to check it out, feel free to give me a follow. And yeah, that's going to be the content every week moving forward, starting next week. Monday, YouTube video. Wednesday is going to be a Medium blog. And then Friday is going to be the second YouTube video. All right, so with those announcements out of the way, let's actually talk about the design. So at first, we're gonna look at some high-level features. Essentially, the design should account for users being able to see their nearby friends online. The friends that they're seeing online should be within 5 miles of the user. That's because these are nearby friends, not just online friends. And the friends should disappear from the list once they become inactive after 10 to 20 minutes of not being on the app. All right, so typically we're going to start with the high-level design and then gradually break it down and talk about the different parts. So if you look at the diagram over here, at a very high level, what happens is that user A is going to send their location to the backend server. The backend server is going to find all the friends of user A from the database. It's going to figure out which of these friends are online. It's going to calculate the distance between the user and the friends to figure out which friends are within that 5 miles radius. Once it knows which friends are online and who's within the 5 miles, it's going to send the update to the friends list so that the friend has the most updated list now. Okay. All right. So yeah, this is what pretty much I go through here. So just to recap, the backend receives the location update from all active users. In this case, we're only looking at user A, but the same thing is going to happen for all active users. For each of the user, when the backend receives the update, it finds all the active friends, calculates the distance between the user and the friend, and then it pushes the update to the friend's device if the friend is online. So I want you to focus on the word over here, pushing the update. That is slightly different to what usually happens, where the client initiates the communication with the server. But in this case, by pushing the update, the server is sending the data to the client. So that's a change. Typically, you have the other way around. So that would be the things that you want to note. The first one is there is going to be a WebSocket connection between the backend and user A. That means in this connection you see over here between the user and the backend server, this is going to be a WebSocket connection. And there is also going to be WebSocket connections between backend server and each of the friends' device. So you see this user A has 3 friends over here. And the backend has 3 separate connections to the friend's mobile devices. This connection, all these 3 connections, they are going to be WebSocket connections. I will make a different video comparing a WebSocket connection to a typical HTTP connection. But essentially, what a WebSocket connection does for you is it creates a long-lasting connection which can be open for a very long time. By doing so, what happens is the client can send data to the backend whenever they want. Similarly, the backend can send the data to the client whenever they want. Typically in a REST API or a typical web app, what happens is whenever the client needs some data, or if the client wants to post new data, it is going to be the one that initiates the connection. And then we have the HTTP connection. So usually it's the TCP connection between the client and the server. And then the client is going to ask the server for the data. The server is going to give the data back to the client. And then the connection is going to close, right? Now, if the server wants to talk to the client again, it cannot do that because the connection is not there anymore. However, in a WebSocket connection, once the connection has been created between the client and the server, the connection is going to stay there for a very long time. What that lets you do is the client can send the data to the server whenever the client wants. And more importantly, the server now has the chance or has the right to send data to the client whenever they want to, right? So that's the benefit of having a WebSocket connection. So yeah, as I mentioned, I will have a separate video explaining what WebSocket connections are and how they work. But hopefully this small explanation gives you an idea of why we want a WebSocket connection over here. All right, so keeping that in mind, by that I mean this high-level design, let's do some very, very basic math. Let's say that your application has 10 million active users. And let's say we decide that each user is gonna update their location every 30 seconds. What this means is every 30 seconds, the user is gonna send their location to the backend. If you do the math, that ends up being around 334,000 updates per second. On average, a user can have 400 friends. I think that's a fair assumption to make. And let's say 10% of those 400 friends are online. So if you are needing 334,000 updates per second, and then of course you multiply it by 400, which is one user can have on average 400 friends, and then you have 10% of these friends that are online. That is around 14 million updates per second. That's a lot of connections and updates to push, because if you remember, all these are going to be WebSocket connections. So if you have one backend server doing all these, of course, that's going to be not only a lot of connections that you have to maintain, but also a lot of updates that you have to push. And you're not really storing these updates anywhere, so they can be dropped at any point. So it's very clear that we need a more sustainable and stateful way to push these updates to the clients. If a lot of these math did not make sense, please put it in the comments. Or if you really want to learn more about it, I would highly recommend checking and buying the book, because the book does an amazing job going into details of all these. All right, so now that we're looking for a more sustainable and stateful way to push these updates to clients, let's talk about how we were going to do that. So if you look at this diagram here, all we're going to do is add in a Redis PubSub system. So imagine Redis PubSub as a system very similar to Kafka. If you remember, Kafka is a messaging bus where you can have producers writing messages to Kafka, and you can have consumers that are reading these messages. When writing a message into Kafka, you can have multiple topics. So let's say Kafka can have 10 topics, and the producer can decide which topic to write a message to. Similarly, the consumer can consume messages from a particular topic, so that the consumers are not consuming every single message in Kafka, but only the messages that they care about, which are defined by different topics. So the Redis PubSub system is very, very similar to the Kafka system that I talked about. Okay. The concept of Kafka topics is similar to Redis Channels. except Redis channels are significantly cheaper to create, maintain, or delete. Kafka topics tend to have some overhead when it comes to creating, deleting, or updating them, but Redis channels are very, very cheap. So you can have a bunch of Redis channels running on a single machine, and it doesn't consume too much CPU or memory. Yeah, so let me take a look over here. Yeah, so if you look at this diagram over here, the only change we made is you have the user A still pushing their location update to the backend server. And now the backend server finds out what friends list needs to be updated. But instead of directly sending it to the friend's phone, what it does is push the location update into this Redis pub subsystem, right? And then there is some consumer that is listening to this Redis pub subsystem, and it's that consumer that picks up the message and then forwards the update to the friend's mobile device. Okay? So this is a better illustration of it. So I'm going to zoom in to make it clear. Okay, I think that should be better. Let me do one level more. Okay, I think that should be perfect. Right. So we already talked about how Redis channels are significantly cheaper than Kafka topics. Now, from here, you can see that the backend is sending or pushing the location update into the Redis PubSub server. And then you have some consumer over here consuming messages and sending it to the client. Now let's dig a bit deeper into that, right? Let's say you have user A, okay, that sends the location update to the backend, and then the backend, so the user A's the backend publishes the location update to the user A channel. That means in our system, every user is going to have their own Redis channel. So if you have 10 users, you're going to have 10 different channels. In this case, we have user A and user B only, so we have 2 channels. So looking at the top example, you have the user A publisher that sends the location update to the user A channel. And now you have another system, so it can be just like a Python consumer somewhere. The consumer or subscriber is only listening to messages coming into user A's channel. Similarly, you have user B publisher, and you have the user B's channel over here. Every time a message comes from user B, this location update is pushed to the channel over here. And every subscriber that cares about user B gets the message or can consume the message. Okay, so that's where I hope you kind of get an idea of how the whole thing is going to work. Is every user now has their own channel, and of course their friend. So let's say if user A, let's look at user B, right? Let's say user B has 2 friends in the system. Both the friends, they are going to have their own subscriber. And as long as they're online, the subscribers can just pick up the message and then update the friends list with this user B's location update. Okay. So this way, what we're doing is abstracting away the concept of directly pushing the update from the one backend server we have to all the friends. Instead of doing that, we're pushing the location update to a message bus, something like Redis PubSub or Kafka, and we're letting the consumers of this Kafka topic or Redis channel take care of sending the update to the friend's device. Okay, so the Redis PubSub abstraction is giving you a place to retain the location update. That's a good thing, because if there's any server drop or connection loss, you know that the data is there in the Redis PubSub system. And you're also doing it in a more sustainable way, because now your backend is not really responsible for as many things, right? You have this backend is only responsible for getting the update and pushing it to the Redis PubSub system. And then you have the consumers that are going to actually pass the update to the client. So by doing so, we are separating the concern. So now, yes, you are adding more components, but you are giving most of these components one responsibility only. All right, so let me read through this then. So each user has their own dedicated channel or topic. Users' location updates are pushed to their own channel or topic. Users' friends subscribe to the user's channel. So if user B has 2 friends, their friends are going to have 2 subscribers subscribed to user B's channel. The location updates from the user are now getting pushed to the subscriber. And then the subscriber sends the location update to the friend using the persistent WebSocket connection that's already there. Okay, so that's how the whole system works on a very high level. Once again, as I mentioned, if you are intrigued by how this works and you want to learn about it in more details, please check out the book. It has some amazing details on how the whole thing works. Now we're going to address a few questions and shape the system to be a bit better. So the first thing is, should we always send updates to friends, right? Because if I am user A, I might have 20 friends, but all of them might not be online, right? Or maybe 10 of them are online, but only 5 of them are within 5 miles of me. So to do that, of course, it would be a waste to send this update to the friend that is not online or is not near me. So yeah, no, we only send updates to friend's client when friend is nearby. That means when sending this update to the friend, we do need a way to quickly access our friend's location data. Okay, that's where the cache enters. With the cache, what you can do is store the location of a friend with a TTL, right? So every location update for a user is going to be stored in that cache. You can think of the cache as a user ID mapped to a lat long, whether like a tuple or string or whatever. And then you store that location with a time to live or TTL of 10 minutes. Currently in this cache, you're totally okay with keeping the data for only 10 minutes because the assumption is that every 30 seconds, the user is going to be sending their location update to the server. Now, if in the last 10 minutes, there was no update from user A, I think you can safely assume that user A is not online anymore. Because if the user was online, they would have sent their location update and the Redis cache would have been reset with a 10-minute TTL again. So yeah, if no location for a user is in cache, we can conclude that the user is inactive. Now, before sending an update to a friend, so this is going to be the consumer that actually reads from the Redis channel and sends the message to the client or to the friend. So before sending the update to the friend, it can look up the friend's location in the cache. If the friend's location is not there in the cache, that means the friend is inactive, so it can just forget about it and not actually forward it to the client. If the friend's location is there in the cache, that means yes, the friend did update their location in the past 10 minutes. Now, using that location data, you can calculate the distance between the user and the friend, and you can forward the update to the friend only if the friend is within 5 miles. Now, the next question is, should we store location data persistently? Over here, if you recall, we are only storing it in a Redis cache with a TTL of 10 minutes. That means a user can have only one. So in the cache, you're only going to have the user's most recent location, and it's going to disappear after 10 minutes. So the question now is, are you okay with that, or do you want to store the location data persistently? More often than not, the answer is going to be yes. You do want to store the location data permanently. you can think of many different features that rely on the user's location. Of course, if you have certain data privacy laws in place, then you don't want to store the location data. In every country, in every product, it works differently. But if you do have the legal right to store the location data, you should do that persistently, because that opens up a lot of options or a lot of features that you can use in your product. Right now, we're only storing it in cache for easy access. And in cache, you don't really need to store all the location data of the user. It's not also very realistic to do that. So we do need a more persistent storage for future uses of this location data. So when it comes to storing the location data, a few things to keep in mind. Firstly, the user is going to be sending the location update every 30 seconds. So each user is going to send it every 30 seconds. And you can imagine if you have 10 million users, that's a lot of location data coming into your system. So of course, that means that these location data, wherever you want to store it, you have to keep in mind that it's going to be a very high write throughput. So if you think about that, there are a few features that your database should be able to handle when storing this location data. The first is, of course, you wanna have such a database that it can handle a very high write throughput. You want to prefer availability over consistency. That's because with the sheer amount of location updates coming from the user, it's totally cool if you're getting the data a few seconds older or a few minutes older, but you should prioritize availability, because you would rather get the data than get the data of the exact current second. All right? So usually in a very high throughput system like this, it's very common to opt for availability over consistency. And then, of course, just by the sheer volume of data, you should have a database that is able to handle it. If you go the MySQL or relational route, you should be able to shard it properly. And ideally, for such a high volume data requirement, you would choose a database that you can scale horizontally. So as your app is getting more and more traction and you have more and more users coming in, the size of this database is going to almost go up exponentially, because the moment one new user comes in, you have that user trying to update their location data every 30 seconds. So you can see how the size of the database can explode very quickly. So you want to be able to scale up or adjust your scaling accordingly. And typically for a use case like that, you tend to use something that can scale horizontally. And keeping all these in mind, so the four we talked about, the best thing that I can think about is to use Cassandra. It's much easier to scale Cassandra. It can handle very high write throughput. And yes, you most probably will sacrifice some consistency over availability. But given you're getting all the other things, I think it would totally be worth the trade-off. When it comes to the schema, I'm not gonna get too much into the details, but you can think of it something like the user ID, latitude, longitude, and a timestamp. All right, so that is pretty much how the whole system's gonna work. Hopefully you got like the main idea of how the system works. Once again, if you want to learn about it more, I would highly recommend checking out that book. I'm also gonna link the notes that I went through in the video in the description below. So if you want that, it's going to be a PDF. You can just download and review it. So I'm going to do one final quick recap, and then we're just going to end the video. So what we kind of talked about today is going to be from the user's perspective. So let's say user A sends their location update to the backend server. This is going to happen every 30 seconds. Now the backend server is gonna take in that request or that location update and put it to a Redis pub sub channel. You're gonna have one channel for every single user. So this location update is gonna go to user A's channel. And then let's say user A has 10 friends. All of their friend, they are going to have a PubSub or a Redis consumer. And these 10 friends, their subscriber is going to be subscribed to user A's channel. This way, whenever there is a new message or a new location update in user A's channel, the subscribers are automatically going to know about it. It's going to receive that location update. Now, what the subscriber is going to do is check if the friend is online or not. It can do so by looking at the Redis cache, which should have all users' location data as long as it was updated in the last 10 minutes. So the subscriber is going to look at the cache to see if for that friend, the data is there in the cache or not. If the data is not there in the cache, then it's just not going to do anything because there's no point in forwarding this update to the friend, given the friend has not been online for 10 minutes now. If the subscriber finds the friend's location in the cache, that means the friend did update the location in the last 10 minutes. In that case, it can pull the location from the cache, calculate the distance between the friend's location and the user's location, check if it's less than 10 miles. If it is less than 10 miles, it can go ahead and push that update to the client, to the friend's phone using that persistent WebSocket connection. If the friend is not within the 5 miles, then like before, it can just drop it and not do anything about it. All right, so hopefully that kind of sums it up. If you have any questions, leave them in the comments below. Once again, most of the ideas I talked about are from this book, The System Design Interview, Volume 2. If you want to know more about how this system works, please check that book out. And also I'm there in the comments if you have any questions. So just leave them there and I'll get back to you as soon as I can. With that being said, I hope this was helpful and I'm going to catch you guys in the next one.